So we're going to take a look at Ohm's Law today. Ohm's Law is going to be basically dominated by the Ohm's Law triangle. So we have our V is our voltage, and that is measured in volts. Yep, I know they're both capital V's. That's great. We have our current, which is going to be represented by a capital I. It just is, so get over it. And R is resistance. Now resistance we measure in this little horseshoe looking thing. All right, it's the Greek symbol for omega, and those are what we're calling ohms. All right, that is the value for a resistor. 50 ohms, 100 ohms, so on and so forth. And then for current, current is going to be an ampere, or we're just calling them amps for short, and that unit is a capital A for amps. So this is Ohm's law, essentially, briefly, in a nutshell. All right, again, how the triangle works, covering up V. All right, V equals, if the two things are next to each other, I times R. If I cover up current, I, V divided by R. And if I'm looking for R, it's going to be V divided by I. Now, in our circuits that we're going to be looking at, this is pretty much, all right, the dominating piece. We need to make sure that we have this, all right, in order to solve for any of our circuit things. All right, so now there are two circuits that we're going to look at, are series circuits and parallel circuits. Today, right now, we're going to just be dealing with series. So in a series circuit, all right, we have a couple different things. So I'm going to just right now write in some of the symbols that I want you to know. All right, so like this little symbol, you have like a bigger line and a smaller line. Okay, this is a battery. And the battery, if we know what that value is, that is very important because that is the total voltage. The total voltage of a system. So if you see like a number to the left of it, all right, so if we saw like a 12 V, that means the battery is a 12 volt battery. That's the total amount of voltage that we have for the whole system. One of the other things, all right, is pretty much this is just our wire. All right, the conductive path, how the electrons are going to move through. This symbol here is a resistor. Okay, these things should have a number above it or below it, and the Greek symbol omega. This is a closed switch. So it is it's part of the wire, part of the conducting path, and when it's closed, the whole thing runs, right? So now if I go to shut the lights off, what I'm doing is, think about this piece right here as like a swinging door. If you're looking at it from above, okay, we open the door, essentially here, the electrons have no longer a path to completely move through from start to end. So when this is opened, whatever we were trying to power, okay, is not going to work. If you see this symbol with an A, all right, usually there's going to be a number next to it, like it could be 2, it could be 0.5, 1, 1.75, whatever. If there's a number here with an A next to it, all right, across any single point of the wire or anywhere in our circuit, this is an ammeter, and this thing measures the current. Measure the current at any single point on our circuit. And then the other one that we'll commonly see, all right, we're just doing the basics. We're not going into crazy stuff. All right, we're not going to really deal with fuses, capacitors, capacitance, diodes, or anything like that. All right, V, this is a voltmeter. And this pretty much is going to measure the voltage or the voltage drop. Voltage or voltage drop across any spot on our circuit. All right, got it? Okay. So if we went back to this, so now we have series and parallel. All right, electric current, continuous flow of electric charge. It flows, all right, when we have a potential difference between 2 points. So if a switch is open, all right, whatever is trying to get powered is going to stop. Close switch, the whole thing would wind up working. A fuse, great. If a fuse breaks, everything that was connected to it shuts down, because then there's no path for the electrons to completely move. So I would show that with this, just a simple quick drawing, or, well, visualization of this. So we have our conductive path, our wire. Boom. Okay, I'm going to add a light bulb here. All right, a light bulb can be the same thing as like a resistor. Connect it not to here. Oops, got to get rid of that, so I got to cut that part. Move over here. Cool. Cool. Okay, and then just for the drawing purposes here. Great. All right, so we see how bright the light bulb is, yes? Okay, now, what happens? What do you think will happen if we add more light bulbs?
A little bit darker.
A little bit darker. Okay, so let's see. Okay, we're going to add another light bulb. Okay, another wire. Boop. You were correct. They got dimmer. Now look at the speed of our electrons going through here, right? Look at the speed of the charge.
Slow.
They got slower. So what do you think would happen if we added one more? It would get even slower, and then what do you think would happen to the level of brightness? It would get even dimmer. So let's see. Yeah. Okay, got even slower, got more dim. So in a series circuit, all right, electrons only have one path to flow through. So when that happens, more components is equal to more resistance. More resistance was a decrease in our current, right? The rate at which these electrons are moving through it. Less current would be less bright light bulbs. And then as the voltage increases, the current increases. So let me see if we can just do that real quick. Can we add a second battery to it? Yeah. Okay, so we added a second battery and the brightness increased. Let's just add, for the heck of it, one more and see what that does. Nope. Yep. Yep, even brighter. Okay, so increasing voltage causes the current to increase, and then an increase in resistance will end up decreasing our current. Okay, so cool with all of that. Let me get rid of this. Let me get rid of this. Let me bring this back. Bring this over here. All right. So we have this. Now, what happens if one of these light bulbs break? Then guess what? You see, there's no longer a one continuous path for these electrons to move. They can't jump through the air, right? They're basically stuck on this wire, this conducting path. So when the circuit is broken or one of those resistors breaks, all right, a light bulb like that, the whole thing goes out. So old school Christmas lights used to be wired like that, and one of the bulbs would break out or burn out, the whole like set would go out, and that was like annoying.
How would they do that?
Why would they do that though? Because it's easier to build. The design is easier, and
Also, you spend more money on Christmas lights.
Combination of that, it's easier for them to build and manufacture. Right, the design's easier, and yeah, if it breaks, then guess what? You kind of need more lights, so come back and buy more.
Also, it'd be thin. It wouldn't be thick, right?
Hmm.
Also, like the wire would be thick, not thick. Right? If
Um,
it was a thick wire, would they have more wires under it?
not necessarily. Not necessarily like a water. Like if you had like a thicker pipe, it's hollow inside. More water could flow through, more charge could flow through, less resistance. That could help, but that was the problem with it. All right. Now it does have its uses, like in a circuit breaker. All right. If you blow a fuse and everything's connected to that specific thing, that's good because you don't want something to draw too much current and overheat. So what happens? Let's see if we get rid of this and we get rid of this. Cool. Let's decrease this resistance a little bit more. Okay, so we have the resistance. Now the thing is brighter, but what can happen is that at a certain point, if the current gets to be too much, the thing can overheat. And then burn out and basically blow up, which we don't want. All right, so that is a series circuit. Now, we need to know how to build a series circuit and analyze it and everything that's going on in here. So what I would have you guys just write down, all right, or what we'll write down is a series circuit. Electrons only have one path to flow through. Okay, so I'm going to write that.
Wait, what do you want me to write? The first one?
Yep, so series circuit. Right, series circuit, the electrons only have one path to flow through. And then we would write in, or I would just have you guys draw in what the diagram for a series circuit looks like. Now they can alter slightly, but for the most part, you're going to have a battery. Okay, what is this symbol right here? A resistor. You got a second resistor. And we're going to have a third resistor. And they can be, right, this is the battery. This could be R1, R2, R3. Okay, so that's all well, that's all good. And now we have the rules that are up on the board. I'm going to just rewrite them here for a series circuit. Yes, there are certain rules. So, in combination with Ohm's Law, when you have to, all right, do or analyze a series circuit and figure out the current at any single point, the resistance, a missing voltage drop, whatever, there are rules that you have to follow. So one of those, all right, we can find, I'm just going to write these. So total voltage is being represented by VT, total voltage. That is going to equal the voltage drop. So think about a voltage drop as the amount of voltage, all right, that's getting used through across each resistor. So that would be V1 plus V2 plus V3 plus, etc. However many there are. If there's only two, then you only need to do it for two. If there's more, you have to do it for that. Then we have total current, which is IT. And IT, the current. Now this is only for a series circuit. Current is the same everywhere. So that means the current going through resistor 1, all right, so I1, the current going through that resistor, is going to equal the current that's going through resistor 2, so that would be I2, would equal the current going through, if there's 3 resistors or, whatever, then, yeah, great. Okay, so if there's more, dot, 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 dot. And then total resistance, sometimes called equivalent resistance, depending upon what source you're looking at. So if you're looking at some books, may say equivalent resistance, REQ. I use total resistance. They're the same thing. All right. So if they ask you for it, this is what they're referring to. So total or equivalent resistance. That will be your RT. That's how I'm going to write it. Some places may use, you may see it like this, REQ, but I don't really like that. I like to just keep everything nice and simple, right? T, T, and T. So the total resistance is literally you add all the values together. So R1 plus R2 plus R3, if there's more, you add them all up. Okay, so with Ohm's law, the triangle that we looked at the top, and these rules, you will be able to solve. You'll be able to solve for any of the missing pieces of information that we need. Okay, is everyone good with this? Bet. So this was an example. Cool. And then what I was going to have everyone do. Where are you? Series. We talked about series. Problem with series. Okay, resistors. Current. Voltage. Some of the voltages across each of the resistors. Great. And this. Okay, so this is going to be like our example problem. All right, so this is going to be our example problem, and so I'm going to draw this in. You guys are going to draw this down as well, so we can all just do this together. Let me move this over here for now. All right, so bam. So they draw this, and this is what they give us. Okay, R1 they said was equal to 50 ohms. R2 they said was equal to 100 ohms, and R3 is 100 ohms. And what else did they say? They said the battery is 12 volts. Okay. So what you guys are going to do from here, is we're going to make a table. Yes, a table. So how the table works, you make a V, an I, and an R. Then, how many resistors do you have? We have 1, 2, 3. So then I'm going to make a 1, 2, and 3. And then we can't forget total. Now, how this is going to work in combination with your Ohm's Law triangle. Okay, so in combination with this, you're going to be able to solve for all of these missing parts. Now, in certain things, they may ask you to solve for only one piece, but if you know how to do the whole thing, solving for one becomes actually pretty easy. So the first thing I always suggest doing is writing in our given information. So right now, all I know is that R1 was 50 ohms, R2 was 100, R3 was 100, and what else do I know? 12. Where do you think that will go?
By T.
Voltage in 1, 2, or 3, or T? T. Very good. Okay. So a rule is you need basically, right, to solve any three variable equation, you need two of the three missing pieces. So if let's say I knew this number was 5, okay, then to find I could use the triangle for Ohm's law, where I would be equal to V divided by R, and kind of work through it there. But for right now, I don't have that. Or for right now, this is all we have. Okay, so we need to use this, and then our rules. Let me see if I can get this to work. Beautiful. All right. Close enough. Dang it. Stay. All right. So in order to solve this, you need to know basically two of the three variables in each row in order to solve for the missing. So that's a problem, because right now I only have one in each. So what do? That's a problem. I can't use the triangle until I have at least two in one of these rows. So I go to my rules. Series circuit. All right, so to find total voltage, I already have it, but I don't know what V1, V2, or V3 is, so I can't find any of those. Cool. Total current, it's the same everywhere. I don't have it at any one spot, so I can't find any of these, but if I look at the total resistance, if I add up all the resistors, I can then find that total. So is there any one spot where I have, oh, wait a minute, I have R1, 2, and 3. So that would be what you would need to do first.
So for 100 plus 100.
Correct. So RT is equal to R1 plus R2 plus R3. So that is just going to be your 50 plus 100 plus 100. And you're going to get 250. So that value, now we can throw here. Okay, so this is the first row that I have two pieces of information. So when that comes up, now I can use the triangle. I have V and I have R in the same row. So I can find IT. So IT will be equal to, according to the triangle, VT over RT. So if I do 12 over 250, that comes out to be 0.048. Amps is my unit. God bless you.
Thank you.
All right, so cool. So where can I put this in? I can put it in for IT, right?
Yeah.
Okay, so that's what I'm going to do. I'm going to put this in, this 0.048. And okay, now that's great. I'm not sure what to do. Let me go back to my rules real quick. Total current. Once I know that, guess what? The total current is going to equal the current going through R1 and R2 and R3. So this is great. The current is now just the same everywhere. So 0.048, 0.048, and 0.048. Okay. And now that I have two of the three variables for 1, 2, and 3, now I can find V1, V2, and V3 by literally just using the triangle.
So I's will always be the same.
In a series circuit, yeah. Once you find I at one point, it's the same everywhere. So now that we have two of our three pieces, okay, to find voltage, we're just doing I times R, but you have to make sure that you're using everybody that is in the same row, or otherwise it won't come out correctly. So V1 is I1 times R1, so you would have to do 0.048. All right, so V1 is I1 times R1. So 0.048 times R50, and this comes out to be 2.4 volts. V2 is,
Is V2 the same as V3?
yeah, they're going to be the same. So it's I2 times R2. So again, the 0.048. This one's times 100. This comes out to be 4.8 volts. And V3 is I3 times R3, or again 0.048 times 100, 4.8 volts. Now, at the end, we always want to just make sure, because our rule here for total voltage is that when you add these up, it has to equal the total. We don't want it to be less or more, so in that case, you may occasionally need to round. But if we add these guys up, it comes out to be 12 flat and even, which matches our total. So then once I know that this matches what my total is, I know that these numbers are good, and I can put them in. So 2.4 volts, 4.8 volts, and 4.8 volts. And then you've literally now just solved for everything in this circuit. This is a nice, simple series circuit. So if you had to solve for any of the other things, any of the other missing pieces, right? If they just said, okay, solve for V1. All right, if we started this thing whole and fresh, well, you wouldn't need to find V2, V3, but you would need to do these two steps. You need to go total to find current, and then if you knew what that is, the current, then you can just do V1. You wouldn't have had to have done these other steps in order to do the whole thing. Okay? All right, so that is our series examples.